Good morning, everyone. Welcome to Lecture 5. So far in this course, we have discussed quite a bit about how we can write SQL queries to answer questions about our data. And we have also talked a fair bit about how database management systems work in order to maintain the integrity of our data. In the last lecture, we've discussed integrity constraints. For example, we could implement checks so that to make sure that the range of our data stored in a particular column satisfies a certain condition. Or, for example, we had foreign key constraints that ensured that when we have multiple tables and we have a column that references another column in another table, we had a constraint to basically automatically check that constraint for us, such that we don't insert any inconsistent rows in any of the tables. So we've discussed both sides of this story, and today we're gonna be exploring a little bit more about that integrity side of things in the first half of the lecture, in the topic of transactions, and then in the second half of the lecture, we will talk about the other side of this course, writing queries. So this is what today's lecture is going to be about. All right, so let's get started. Okay, so starting with transactions. So let's consider that I owe my friend Joel $1,000 and I want to transfer money from my bank account to Joel's bank account. And in terms of the banking app and the database management system that the bank uses, this operation involves these two steps. Deducting or debiting $1,000 from my account and then adding that $1,000 to Joel's account. So there are these two parts to it. And we have learned how to do this in the previous lecture in SQL. That's the first step, so debiting the first account, update this account's table, and then set the column balance to balance minus 1,000, that's my account, where account number equals a certain number. Suppose that that's a very simplified version of what I want to do in SQL. Makes sense? Okay, that's the debiting part of my my process. And then I have to add $1,000 to Joel's account. So again, I update the accounts table and set the balance column to balance plus 1,000 to take that into account, where account number is, for example, suppose that this is Joel's account number. Okay, so there are these two steps. All right, but now, something that happens in the real world is that we might have a power outage between these two steps. And then suppose that the power outage happens right in the middle here, and then my account would be left debited $1,000, while Joel has also received no money at that point. So there's a loss of money, and the net amount of money in the system is not conserved. And that's a huge concern. Okay, so how does SQL actually address this? And for it to make realistic sense, you have to consider that there is not just one such financial transaction happening at any moment. There might be thousands of such transactions happening, so the probability of some kind of database crash makes more sense and seems more real. It's not just this one case. Okay, so this example illustrates a case where we want either all of the above steps to be done, all of those changes to be done, or none of them to the database. So in other words, we want this whole thing to be treated as a single logical unit of work. In database terms, we call this whole process a transaction. So a transaction is a series of steps of database operations that I want to be done And the point about calling it a transaction is that either all of it is successful, all of the changes are made to the database, or none of them. So if the transaction, if the top part just fails for any reason, then the whole operation becomes aborted. I will not be left with some half-baked operation on the database. That's called a transaction. All right. So let's see how we can actually define these steps inside a transaction in Postgres or in SQL in general. So we will have a syntax like this. So begin transaction. And then we have the SQL statements that we had before. Update account set balance minus 1,000. Update account set balance plus 1,000. Everything just the same. And then at the end, we have this commit keyword. So it starts with begin transaction and ends with a commit. So pretty much like the kind of commits that you do to a GitHub repo. When you do the commit, you make things permanent in the database in your repo, for example. Okay, now that we do that, if these statements fail at any point, then the whole operation becomes aborted, and that's exactly what we want. All right, so here is the overall structure of a transaction in SQL. Begin, you can either use the begin keyword or the start keyword, that's up to you. Both are acceptable. Transaction, that's optional. And then a bunch of SQL statements that you want to have, followed by either a commit or a rollback keyword. Okay, so note that this whole begin transaction or start transaction thing, the whole keyword is, the whole set of keywords is optional. You can have it if you want to make it more obvious to the reader that this is something that you want to do, you want to make a transaction, or you can just ignore that. But the commit or rollback is necessary. Okay, so what's the meaning of commit? What's the meaning of rollback? Just as I said, when we do a commit, we want all data modifications during the transaction to be made permanent in the data set. And rollback is the opposite of that. All of the changes made during the transaction, we want them to be discarded, and we want the database to be restored to its state right before that transaction. Okay. So now let's have a look at an example here. Okay, same MDS database and then the code for populating the tables. Again, you just run that. You don't need to read through that. And then let's have a look at the instructors table. Okay, same as before. All right, and now I'll also establish a connection to the database using PsychoPG2. So this connection is through IPython SQL. As you know at this point, I established that connection here using this connection string. And this is my connection through Jupyter Notebook. However, this is another connection made through PsychoPG2. So there are two connections to the database at this point. Okay. All right, so here I'm trying to run these set of SQL statements using PsychoPG2. You have learned how to use the code here in your labs. And okay, I begin a transaction and then I update the instructor table and I want to set the phone number column to null. Just basically get rid of all of the values inside of this phone number column. I want to set all of them to null. Okay, let's do that. All right, now let's see. So here I select everything from the instructor table. Okay, we can see that the phone number column is set to none for all of the rows as we expected. Okay. Now, what's the purpose of this example? I want to show you that one thing that the database does through using transactions is that it isolates operations from different clients from each other. So when we make such a, we try to make such a change in our database, the database actually locks a table or a collection of rows, and then until that particular transaction is finished, the other client does not have access or is not aware of the changes made to the database. So right now, I have begun my transaction. I've updated the instructor table and set the phone column number to null, but I haven't finished my transaction yet. I haven't committed the changes to the database yet. Okay, so what I expect is that if I look at the database through the eyes of another client, I should not see those changes. So I have these nones, but if I check out the database through this IPython SQL code, that's a different client. And if I run that, I can see that the phone numbers are still there. Which means that if my transaction fails, this is what exists in the database, and this is what I will have. So this transaction is not yet committed. The changes are set to be not durable yet. Okay, now let's see what happens if I commit the changes. So I run this simple SQL statement, commit followed by semicolon. And if I do that, now the changes are made permanent. And if I check out my database again through the eyes of the other client, I will see that the changes are made to the database. Okay. So again, this example was to show you that database management systems isolate different transactions from each other made by different users. And until the moment that you commit those changes and you make those changes permanent in the database, other users are not aware of those changes. This is because suppose that you're doing some kind of operations on your rows, you're making a bunch of changes, you don't want some other user to interfere with your changes while you are working on your database. This is something pretty basic to expect from a database system. It's not, the implementation is actually pretty involved. It involves a lot of technical stuff that we won't go into, we don't have time to go into, but this is a basic expectation that we want to have. Okay. So, questions so far? Yes. Yeah. So question is, what if two clients make changes to the database at the same time? So same time kind of never actually happens. The person that makes these changes is either like earlier than the other person or later than the other person. So there is an order to that. And then the database places a lock on the rows and the tables that you're working on. And until that lock is released, the other transaction does not go through. Yeah. Yes?
Just a little what he asked. If we have, for example, a complex query, and it takes some time to do, and we have several people trying to access that database with this noise, does it make like a queue for each one of them?
Mm-hmm. Okay, so if we have a query or some database operation and it takes a long time, what happens in that case? So if you really pinch me and ask me what happens in reality, the thing is the isolation is not 100%. So the database decides which parts of the rows you can actually modify, the parts that are not under a certain operation at this moment, and then the other parts are free, you can make changes to that. But this is programmed and designed in a way that consistency is still achieved. So isolation can have multiple different levels. This is usually not full isolation until you actually prescribe that for the database. So yeah, so there are different levels. Yeah. Okay. All right. So similar to this commit SQL commit statement, we can also do the commit using the connection object and then do .commit followed by open close parentheses. This is just as an FYI. Now let's see an example of rollback. So here I begin a transaction and I say, okay, delete from instructor, And we know from previous lecture that if we do this delete statement without any where clause, then we delete everything because there's no condition. So let's do that. Okay, delete everything. And now let's look at the instructor table. Expectedly, there's nothing left in the instructor table. Okay, now if I do rollback, I can abort all of those changes and then go back to the previous state. So do rollback and then select everything from the instructor table again, and here we go. We have everything back at its initial state. Okay. All right, so when we use PsychoPG, PsychoPG2 package, which is the official Python driver for Postgres, by default, when you even start a select statement, that begins a transaction by default. Every SQL statement begins a transaction automatically, and unless that transaction is committed or aborted or rolled back explicitly, that session remains open. And until that session remains open, you cannot do anything else, pretty much anything else, to the database. So it's important that you either commit or abort that particular transaction. So in order to avoid having these long-running transactions, we can do one of the following. We can follow one of the following steps. So either we put our DBMS in auto commit mode, meaning that as soon as a SQL statement ends and you hit a semicolon, just commit the changes right there. Don't wait for the user to issue a commit statement in order to make the changes permanent. The other thing is that we can use this with constant context manager inside of Python. You probably know this with structure in Python from when you've tried to open files in Python, right? And the thing it does is that within the with statement, you do everything that you want, and as soon as you exit that block, the resources are released. So that file, for example, if you have a file open in Python, then the file will be closed as soon as you exit that block. Here, it works in a similar fashion. So with a database connection, when you execute a SQL statement or a bunch of SQL statements, as soon as you exit that block, then the changes, if they're successful, there's no error, the changes will be committed, or they will be rolled back if there was any errors. So that's the whole. This is why in Lab 1, yes, in Lab 1, you see this with statement in some of the questions. This is the syntax that I have used. Because if you don't do that, you will begin a transaction, and you will not commit the changes unless you issue a commit statement. And we didn't learn about that, so I just used this with context manager. Okay, so when I do this, for example, delete from instructors, you can see that because I exit that block immediately, this is run, and then I exit the block. Now the changes will be immediately visible to us, even without issuing an explicit commit statement. Okay, with IPython SQL, it runs in auto commit mode by default, and this is why we don't have long-running transactions. So you saw with PsychoPG, we have the with context manager. With IPython SQL, it's already in auto commit mode, because so far we didn't really need to use transactions. But you can change that if you want. Okay, questions? Yes?
Does that mean all requests are transactions?
Yeah, any SQL statement that you run is a transaction. Any other questions? Yes? Can you speak up, please?
When you roll back, does it roll back the last commit or last transaction?
Oh, question is, when you roll back, does it roll back the last commit or the last transaction? So the rollback works inside of a transaction, And when you issue a rollback command, then it just rolls back the changes made during that transaction up to the first point. Yeah. Okay, so usually the rollback, we usually don't need to explicitly have a rollback statement in our transaction because we usually want the changes to be committed. And if the statements, the SQL statements are not successful and there are any errors, then implicitly the database management system just does the rollback for us. So what would be an example or maybe two examples of situations that we may want to issue a rollback statement explicitly? Can you think of any? Yes. Okay, so the thing is when you make the commit, it is possible to go back to a previous commit but not using the rollback statement. So it's only within a transaction. Yes?
When the transaction is working with multiple tables and for some reason one of them is not available or throws an error, that way we are not making changes to the other ones before the
That's true. That's true. Yes, yes. We were working with multiple SQL statements, and one of them hits an error, and we don't want changes to be made permanent, and we use a rollback. So there could be a few reasons. Maybe you want the person who reads your query to explicitly know that, hey, we're doing a rollback when this is not successful. Otherwise, it's implicitly rolled back or aborted. So one situation would be when I want to just test something and I don't want to make the changes permanent. So I test something, and because I am right in the middle of a transaction, I can still check out my database as if the changes are permanent, and then roll back whenever I want. So that makes like a good kind of strategy for us to test things out. Another situation is that usually when you work with databases and you connect to them through Python as for example, a backend of some system, we don't write all of the SQL commands in just one long string and then run them all. Suppose that we begin a transaction, we run just a piece of SQL statement somewhere, and then we do some Python coding. And suppose that in our Python code, we see some error. And then we see that error, we want the operations to be rolled back. And then in that situation, we can use the rollback statement, right? So it's not always, the error might not always happen within the SQL statements. It might happen in your backend programming language. And that will be helpful for that situation as well. Okay. All right, so how does all this this transaction work? So, for example, when I say that we make the changes, but we are actually not making them permanent, we can roll things back. How does that work? We won't go into much detail about this, but it's I guess it's useful for everybody to know that a database keeps history of all the changes made. Excuse me. Made to the database during a transaction, and basically logs everything and stores that information in a log file, sequentially writes that log file as a history of things to keep track of things. And because we're keeping track of things, we can go back to the previous state whenever we want. We just undo the operations one by one, and we go back to the original state. And this is why, because the log file is such an important thing, it basically make sure that we have a history of what we're doing. In real-world applications, the log file is usually kept on a different physical hard drive because that's super important. You might have a backup of the database somewhere, but even if the data is lost, you can use that backup. But if the log file is gone, then everything about the transactions are gone. Okay, so now let's talk a little bit about this wall technique. So there is a technique commonly used in database management systems called write-ahead log or wall that records changes to be made. I'll be back. Records changes to be made to the database within a transaction in the log files before actually making the changes to the database that's stored on the disk drive. Yes.
Just wondering if we have the transition log, that's the SQL
Oh, okay, good question. So if we're keeping a log, then if we have a SQL injection attack like we saw in the previous lab, can that be reversed? Yes, technically yes, that is possible. But usually when the person doing such an attack, they usually hack into the system and create an admin user for them. And then they disable probably those logging operations or delete some of those logs or initial states. So it doesn't just end there. Yeah, that's the thing. Yes, we can go back in time. There is an option to basically a point in time recovery that I have here on the screen. So what happens is that when we are trying to make changes to the database inside of a transaction, instead of at each step, instead of writing the changes directly to the hard drive or to the disk where the data is located, we just keep track of the changes and write a history of those changes, description of those changes to the log files. And then once the commit statement is issued, then we start writing to the disk. And that's because if somewhere in the middle of a transaction an error happens, the system crashes, there's a power outage or something like that, if we have written some data to the disk, then that can cause inconsistencies between the actual state of the data and something that we're in the middle of doing. So basically, we do not write anything to the disk unless we're sure that this transaction is ended. And the thing is, even if there is a power outage, because we keep the log sequentially step by step, then when the system comes back on, we still know, okay, these were the steps that I was trying to do, so I can just undo them. I can just remove those steps from the log file. That's all that's needed to be done. So using the log files can avoid having inconsistencies in that way. And the other thing is that we probably might not need to have so many disk writes. So instead of writing things to the disk at each step, we wait until the end of the transaction because we might change a bunch of data and then maybe revert some of them back to their initial state or something like that. So we don't want to write to the disk immediately as we see when we see a SQL statement. So in this way, we wait until the end and say, hey, make up your mind of what you're trying to do, and then I'm going to write the changes to the disk. So this is another purpose of using this write-ahead log technique. So for us to know, the important thing for us to know is that there is a log file being kept, and that helps us to keep a track of things that we're doing inside of a transaction, and it makes sure that if there is a power outage or system crash, we can still keep the system in a consistent state. Okay, questions?
So since we have the auto commit being true, so it means that we have the log of all of our queries?
Okay, so question is, since we have auto commit equals to true by default, does this mean that we have a log of? Yes, there is a log of all the queries available, and also the important part about that is not the log of all queries, probably. The most important part of it is that we have the log of operations within a transaction, but that is also kept as well, yes. And that is actually what helps us to have this option of point-in-time recovery, meaning that if we have the log files and we have a state, a backup snapshot of the database at some point in time, then we can take the initial state and then take the log file and replay the changes until we get to the end state. Yeah. Okay. All right, let's move on. So what is the implications of integrity constraints for transactions. All right. So in lecture 4, we've learned that there are some integrity constraints that we put on our column values, and then I didn't tell you that some of those constraints can be made to behave differently inside of a transaction block. Let's consider this example here. So suppose that I have to populate the table again. Okay. So because I've deleted everything, so let me do this. All right. Let's go back here. Okay. All right. So we have these two instructors, Mike and Tiffany. And then suppose that I want to swap the IDs of these two instructors. So Mike has ID of 1, Tiffany has the ID of 2. I want Mike to have ID of 2 and Tiffany ID of 1. Pretty simple operation, seemingly. Okay, if I do something like this, so update instructor set ID equals to 2 for Mike. This is Mike. Mike has ID of 1. Okay, if I set that to 2, what do you think happens? Yes, ID is a primary key, has a primary key constraint on it. So it should be unique. Okay, so it gives me an error saying that this column cannot be non-unique. So let's run that. Yeah, as expected, yeah, it says that an error happens here, basically. Okay. So what can we do to actually make such a change? The thing is, inside of a transaction, we can momentarily or temporarily ignore some of the constraints, okay? And we can make this possible by defining different set of constraints, basically adjusting them to make this possible. And we have a set of keywords that makes this possible. For example, in our create table statement here, if I have, okay, ID, integer, primary key, and then if I follow that by deferrable, initially deferred, this means that I'm allowing that constraint to be ignored while I am inside of a transaction. And that's actually exactly what we want, right? I want the database management system to ignore that uniqueness on that column just for a moment. Just let me do this change and I'll make sure that this remains unique afterwards. This is what we're trying to say. Okay, so we can do that using these two keywords, these two set of keywords. So this one, deferrable, initially deferred, means that this particular constraint will be enforced, but it will not be checked until the end of a transaction. That's straightforward. There's another set of keywords that does something similar with a tiny difference. So deferrable, initially immediate, means that the constraint is there. I'm still going to check that unless in the beginning of your transaction you say set constraints deferred. Unless that you're explicitly telling me, hey, this transaction is an exception, I'm going to enforce those constraints, just as before. So these two set of keywords can help us achieve what we want and what we need. And we can see that in action here. Okay. So here, instead of recreating the instructor table, which is something that might not be an option in real life, we just go ahead and use the alter statement that we have learned before. I'm going to open up the terminal here to show you what kind of constraints we have at the moment. So let me connect to, yeah. Okay, connect to MDS. All right. And then the instructor. Okay, so right now the only constraint that we have is a primary key constraint on the ID column. So what I'm doing here is that I say alter this table, and what I want you to do is to drop that particular constraint. This is the name of the constraint, which is automatically given, and you can see that here. So drop that, okay? And then, again, alter that table and add this primary key on the ID column with the difference that now set it to deferrable, initially deferred, meaning that, okay, enforce this constraint, But wait until a transaction is over and committed, and only then check that constraint. Let's run this. And then let me run this psql command again to see the difference. It says, okay, primary key, however, it's deferrable, initially deferred. So you have basically made that change. Let me close that. All right. So now here I have a transaction similar as before. Update the instructor table, set ID to 2 for Mike, which had an ID of 1 initially. That violates the constraint, but that's okay because I have set that constraint to be deferrable until the end of a transaction. Okay? And then update instructor again, set ID to 1 where name equals Tiffany. So, okay. Now I have been able to make that change without violating the constraint temporarily. And then finally do the commit. So now, because the constraint is deferrable, I run this, it works. And then if I take a look at those rows, all right, now I see that Mike has an ID of 2, Tiffany has an ID of 1. So this is a use case of making constraints deferrable inside a transaction. So this is an interesting use case for using transactions. You can temporarily violate your constraints while you're doing something. But at the end, your database should still remain consistent and the integrity constraints should still be enforced. Yes?
So in each transaction, those queries are referring to the original database, right?
Yes, the state before this transaction is happening, basically.
So like, for example, for this particular query, we had like setting the ID of Mike to 2, and then once we want to set the ID of Tiffany to 1, this query refers to the original database.
No, okay, no. So the thing is, while we are inside of that transaction, we are writing those changes to the log files, and within that transaction, it deals with the updated state.
Okay.
But it doesn't make the changes permanent to the database itself. Yeah.
So let me rephrase my question this way. What if I want to swap the IDs? Not just assigning them. Because I think we are using set. So we are setting set ID equal to 2 and then set ID equal to 1. What if I want to swap them? What if I want to say the ID of like Mike should be assigned to Tiffany and Tiffany to Mike?
Yeah, I guess, okay, so the question is, what if so here we're doing the swapping manually.
Yeah.
You want that to be made kind of automatic. I guess we can we can use something that we're going to be learning in the next part of this lecture. We can use a subquery to read the database at this point and then obtain some information and then use that. We can do that basically, yes, that's possible. Yeah. Yes.
Whenever you want to use that deferred immediate from the deferrable state, is it going to be more like specific for what you're doing?
Yeah, so you're talking about the other option. So the other option is that we basically want to have, let's say, more control and be more strict with what we're doing. So we say, okay, unless the user explicitly tells me, hey, this is a situation that I really want to ignore that constraint for a moment. So until then, we still enforce that for every statement. Yeah. Okay. Other questions? All right. It seems like a good, nice moment to have a break. Let's take a few minutes and then be back in 4 to 5 minutes. All right, we are back. So, before jumping into the next section, talking about subqueries, there's one last thing remaining that I need to talk to you about, and that's this ACID property of a database management system. This is something that comes up a lot. Usually people say, hey, this database management system is ACID compliant. And now we have actually learned all of the fundamentals to understand what ACID means. So let's start from the first word for that in that acronym. So ACID stands for atomicity, and then consistency, isolation, and durability. Let's see what all that means. So atomicity means that what we have basically discussed about transaction, either everything inside of that transaction happens or happens and will be recorded, or none of that will be recorded to the database. So all or nothing, meaning that we have atomic units of work. It's a package. We have to accept it all together or none of it. Okay, so that's atomicity. What about consistency? So, just as I was kind of implicitly implying, although we can ignore constraints, integrity constraints within a transaction, but I mentioned that the database management system still enforces all of the constraints as soon as the changes are committed to the database. So we can ignore some of them temporarily inside of a transaction, but those constraints will still be checked whenever you're trying to commit your changes, meaning that your database, the data that you are storing, will always remain consistent based on the constraints that you have defined. That's the meaning of consistency. So that's the second letter. That was A, atomicity, and then consistency. And what's the meaning of isolation? Something that I discussed right in the beginning of the lecture. So isolation means that different transactions are isolated from each other, although to different levels, but they are isolated from each other to the extent that we are sure that some changes from another transaction does not interfere from this particular transaction that I'm working on. Meaning that if two clients are working on a table, we are sure that the transactions that they're working on will not interfere each other. That's the meaning of isolation. Okay. And durability means that the changes that are made by a successful transaction will be permanent. Even if you have a transaction and then somewhere in the middle you commit the transaction, but there's a crash and the system shuts down. Even in that case, because the log file has been updated, when the system comes back on, it goes back to the log file and sees that, okay, these changes have been trying to be committed, and the changes on the hard drive does not reflect that. So let's replay those changes and make that commit. So as soon as you have a commit that's actually recorded in the log file, you can be sure that your changes will be reflected in the database. And if somewhere in the middle that transaction is broken, you can be sure that it will be taken back to the initial state. So there is no middle state, never. Either a transaction will be done completely or it will be aborted completely. That's the meaning of durability. So when they say that a database management system like Postgres, like Microsoft SQL Server, like Oracle DB, when they say that this is ACID compliant, this is the meaning of it. So there were times that some versions of Postgres, for example, didn't satisfy one of these particular properties. So it doesn't come naturally to a database management system. There's a lot of work that goes into ensuring that these properties are actually there in a database management system. Pretty much all SQL-based relational databases are ACID compliant. Examples of cases where a database management system is not ACID compliant are the non-relational databases that we start discussing in Lecture 6. And the basic reason that they're not ACID compliant is that with relational databases, you usually store everything in one giant server, one computer. That's usually the case. However, with the new non-relational databases that store big data, huge amounts of data, we usually distribute that data across multiple servers. And in that case, it will be a mess to keep track of all of these transaction-related properties. So they satisfy some other different types of properties, but it's not exactly ACID, just as an FYI for now. All right. I think now we're ready to steer away from this discussion of transactions. We can start working on the topic of subqueries. So up to this point, we've been again discussing about basically the integrity of a database, the integrity of the data in a database. And now let's go back to our sweet discussion of writing queries. Okay. Now comes the more fun stuff. So we discussed that a query like this, for a question that we see at the above, find countries with surface area above the average value of all countries in the world. This query will not work. Select name from country where surface area is greater than average surface area. And what's the reason for that? Pardon me?
It's right there. Aggregate functions can't be in a way.
Yeah, it all goes back to the diagram that I showed you. Okay, the aggregate functions, when the where clause is being processed, it has no clue about aggregate functions. That can't be done. Okay, so now we finally learn how to do that. We need to use a structure called a subquery, meaning as a query within another query. So if only we had a way to actually compute the average surface area somehow and then plug it into this query, then it would have worked, right? So a subquery does exactly that. So in one of the labs, I asked you to compute some value in a query and then manually take that value and put it into another query in order to answer a specific type of question. So here, you no longer need to do that. We can actually do something like this. So select name from country where surface area greater than what? Greater than the result of this query. Right? Select average surface area from country. Simple as that. That comes back as a number. That's the average surface area for all countries in the world. And then this outer query will be just select name from country where surface area is greater than a number. And that works without any problems, right? This is called a subquery. And it makes us able to answer much more complicated questions using SQL queries. Let's give it a try. Okay, same query here inside of a SQL cell. Okay, it works without any problems, without any errors. These are the countries that have a larger surface area than the average global surface area. Yes? We can use the having clause to answer this same question. How can we do that? So if we use the you group by surface area. Does that really work? So group by surface area, there are a bunch of different numbers, right? It just returns the same table back to you. So, yeah. Any other questions? Okay. All right, so a few points about subqueries. The subqueries should always be enclosed in parentheses. That's one. And you should not terminate subqueries by semicolons. Okay, as you can see over here, there is no semicolon here for this subquery. That's the second point. And as I just mentioned, we call the bigger query the outer query, and sometimes the subquery is called the inner query. So this whole thing, this thing, and these parentheses, this is called the outer query, and this thing inside is called an inner query. Just the terminology. Okay. Where can you use subqueries? You can use subqueries in the select clause, in the from clause, in the where clause, in the having clause, pretty much everywhere you want. But there are certain constraints that have to be met. For example, subqueries used in the select clause cannot return rows or columns. They should be just a single value. Okay, now suppose that in our last query, we also wanted to, as a confirmation, we wanted to compute the surface area of a particular column of a particular country to the average surface area of all countries in the world. So basically we want to compute the ratio. If that ratio is greater than 1, it means that our query is actually correct. So you can run the same query. You can see that all of these numbers are greater than 1. So you can see that I have used a subquery here right in my select statement because this whole thing returns a number. Okay, so round surface area divided by that number, and then run another subquery here to basically apply that filter. Does that make sense? Any questions? Yes.
I see in this code that you're repeating the subqueries.
Yeah.
Is it possible to have like something that only calculates once instead of calculating?
If it's the same thing. Not as a part of SQL standards. Some of the database management systems actually let you define something like a variable or something and store the results there. In Postgres, there is probably something like that. I'm not aware of it, but it's not like part of the standard SQL practice. The other thing is that if you run that query, the database management system actually caches some of those values. So you can be sure that performance-wise, you're pretty much safe. Yeah, if it's exactly the same query. Yeah. Okay, let's move on. So let's take a look at this query here. Retrieve the name of countries whose capital cities have a population larger than 5 million. Okay, so you can see already that this subquery thing makes our job much easier because we can write queries in much more intuitive ways, right? We can say, okay, select name from country where the capital, which is a column inside of our country table, which just contains the ID of the capital city. So you say, okay, capital ID in what? In this list of IDs. And what is this list of IDs? What does this return? The ID of cities that have a population greater than 5 million. So we say that whenever the capital ID is inside of that list, then you can return that row to me. It makes a lot of intuitive sense, basically, right? So question, does this condition where capital ID in something remind you of anything you learned in 512? What are we doing in terms of algorithms and data structures? Yes, we're doing like basically something that we sometimes apply linear search to. Right? So we're trying to see if a value exists inside of a sequence or a collection, right? Okay. So what is its implication? Where this subquery returns a bunch of values, meaning that it returns a list, and when we loop over those rows inside of the outer query, we basically take that value, take that capital value, and do something like a linear search every time. So in terms of complexity, what would be the time complexity here? I don't want like exact terms here. Just tell me like if it's linear, logarithmic, polynomial. You can assume that country and city table have kind of the same size. Suppose that they have n rows, each one of them. It will be, yes, it will be n squared. Okay, so that will be very inefficient, right? Okay, good thing is that because SQL is a declarative language, we just, most of the time, when we say that we want something like this, we usually don't have to worry about performance that much, because in most common cases, the database management system, the engine, actually figures out, hey, this will be a very inefficient query, and it actually does something else to return the same result to you, okay, in order to make it more efficient. So, can someone tell me, can we write this query in any other way to answer the same question? Without the subquery. Yeah, we can use a merge or join, right? We can join the two tables and then apply that condition. And if we do that, if our merge operation is a little bit more efficient than what we're doing here, then that's a win, right? So that is actually what, so we can do a join like this. It returns the same results. It's 13 rows, and here we also have 13 rows. Okay, so I'm going to show you one interesting thing that you can use in order to find out what the database management system actually does. So we can do pg admin 4. Okay. All right. Okay, now I'm going to go to the world database, open up a SQL query tool, and I'm going to paste the query here. Okay, all looks fine. Now, instead of running the query, if you click this explain button over at the toolbar, okay, I have to get rid of that SQL thing at the top. Okay, if you click explain, it shows you something like this. Okay, so this is what the database management system actually does. Although you have told the database, hey, use a subquery here, but the database management system figures out that is inefficient, that'll be polynomial in time, so it's actually gonna, so you can ignore the hash thing, it actually does an inner join in order to answer the same question. Okay, and that is more efficient. The way that it does that is that it takes the smaller table in the subquery and basically creates a hash table of the column that we're trying to join on. And then uses that hash table to join it onto the other table, the bigger table, and now we have done an efficient merging of the two tables. It's no longer polynomial. Now the only thing that we have to do is to do a linear search to filter out the results that we have. So linear in time and something close to, yeah, again linear in time with a hash join. So this is something that happens all the time. When you're writing queries, especially complex queries, the engine figures out the correct way to do that, and it might not actually do what you expect it to do, but it returns the same results to you. That's guaranteed. Okay, we'll discuss this a little bit further in the next lecture, but this is, I think, an interesting point in terms of efficiency, what the engine does for us. Questions? Yes?
Do you have any control over the way that engine interprets the code?
Do we have any control over the way that the engine interprets the code? To my knowledge, no direct control, but we can write our queries in a way, sometimes, in a way that we actually can enforce a particular way of execution.
And also, is there any difference between different flavors of SQL in interpreting?
In terms of how they do this, yes. Yes, there is.
So it depends, like which flavor.
It depends. Yes, but for such operations, they pretty much do the same thing, all of them, because there's not many ways to achieve the same thing. Yeah. Okay, let's go back to, where was it? Okay, so let's move past this. All right, so subquery is another way to gain access to data stored in other tables, just like joins, but that's not the only use case for it. We can use subqueries on the same table. But again, this is an alternative way. So if joins can be written as a subquery and vice versa, what's the difference? just as we talked about, subqueries tend to be more intuitive and readable to write. And there are actually some questions that you cannot answer with a join. Absolutely. So in those situations, we have to use subqueries. All right, so I have a bunch of examples here that I think it will be, for example, we can skip this one, and I will make sure that we go over these examples in the lab. But let's discuss the next topic here. All right, correlated subqueries. So what we have learned about in the past few minutes, our subqueries are called simple subqueries because the subqueries is going to be processed once, and the result is received, and then we take that result and work with it inside of our bigger query. Okay, so the point here is that the subquery is executed once. There are a set of results, and then we work with that. However, sometimes for certain questions, we cannot do that. We cannot pre-process things. We actually have to dynamically take, for example, each row and do something in a subquery, and then take the other row, do something else in a subquery. In these cases, the two queries have to be connected to each other in some way. And we'll discuss how. They have to be able to communicate with each other. We call these queries, we call them correlated subqueries. Let's see an example of that, where that can be helpful. So which countries have the largest population in the continent where they are located? So think about this question for a moment. Which countries have the largest population in the continent where they're located? So it's not asking about like all continents on Earth. It's specifically asking about the continent that a particular country is located in. So you can say that when we take a row, we look at a country, we look at its continent, okay? I want to find the countries, return the rows for which they are they have the biggest population. So I cannot look at all the rows. I cannot pre-process things. I have to take this row and then look through the table to find all the countries in the same continent, compute the population, compare that population to this population. That's what we have to do, right? There's no other way around that. So in this case, we should use a correlated subquery. And let's see how. Okay, let's take a look at this query for a moment and see what's happening here. So it looks like we have a subquery down there. Okay. And then we're selecting a bunch of columns, doesn't really matter. We're pulling data from the country table there, and then we have a where condition. We say, okay, return the rows from the country table where the population is equal to something. And that something is the maximum population of countries that happen to be in the same continent as the one in the outer query. That's a lot to digest, I know. That's a lot to digest, but this is what it is. So it looks at each row, takes that row, and then goes into the table again, looks into the table again, and says, okay, for example, suppose that we're talking about Japan, okay? It says, okay, I'm taking Japan, and now what countries are also located in Asia? It says this country and that country and that country and that country. Okay, it says compute the maximum population for me among those countries. Okay, one country comes back. And then it says, okay, now only return Japan in the results to me if that is equal to the maximum population country that you have just computed. And then goes to the second row, does exactly the same thing, looks at its continent, and then looks at all countries in the same continent, computes the maximum population, checks for equality. If this is actually the country with the biggest population, it will be in our results. Goes to the third row, does the same thing. Goes to the fourth row, does the same thing. So for each row, it looks at the table once again and does some computations. So you can already say that a correlated subquery could be pretty inefficient, but it answers some very interesting questions. Now questions.
This is going to take time, but we say country space C1, same as country.
Yeah, okay. Yeah, so about C1 and C2, just like when in joins, we alias them in order to refer to them in a more concise way. That's just an alias. So country C1 means that I have to use C1 to refer to the country table. Yeah, you can like ignore the as keyword. You don't have to do that. Yeah. So C1 population means I'm taking this row, I'm looking at its population. C2 population relates to the inner table, the one that we're taking for the correlated subquery. Okay. That's a lot to digest, but hopefully I've given you like enough information to think about it and then figure it out. Okay. Now let's take some questions. Yes.
So for our inner query, can we use like grouping by?
Okay. So question: for our inner query, can we use some group by statement?
By continent, and then report the maximum population, and then take the output of this subquery and then put it in the same query, saying, okay, for this continent, report the country name equals this population.
Yeah. So the question is, can we use a group by here to maybe do it more efficiently? Something like that. So whatever is possible to write in a query, you can also do that inside of a subquery. You can do a group, whatever you like, as long as it makes sense in terms of like the aliases that you work with and everything related to the outer sub. So you can do anything that you like as long as it's consistent with the outer subquery. Yeah. So a subquery is just a valid SQL query. It can be anything. Any other questions? Yes.
Are you able to access the result
Access the result of the max outside of that. Yes. Yes, we should be able to do that. C2 population. Or maybe I should correct myself. No, I don't think so. I don't think it's possible in this form. No. Yeah, we cannot list. Maybe. Okay, I'm not sure. Let's try something. Just if we do something like this, I'm just curious. That's an interesting question. Nah. Okay. Yeah. No. Not in this form. Not in this form. There are ways around that. There is another way to do kind of similar things that we learn about in the next lecture. In that form, it is possible to return values like this, but not in this form. Yeah. But great question. Okay, so we have a bunch of examples that come after this one, and we don't have time to cover them today, and I anticipated this. That's perfectly fine, but rest assured that we will cover all of that in the lab or in the beginning of the next lecture, so don't worry about time. Maybe we have time to cover perhaps one more example. Let me see which one is a little bit more interesting. All right. Oh, okay. So we discussed this question in the lab actually as one of the activities. So use a query to return the name of countries whose capital city is not their most populated city. We worked on that activity question in the lab. So let's see if we can answer that question in a subquery. So the way that we can do this is that first we join the country and city tables to have access to the countries and their capital cities. That's the first step. So we just want to have access to all of the information in one place. Okay, so countries, their capital cities. All right. And then we can take the same query and then now use a correlated subquery to basically check that condition. So going back to the question, find the name of countries whose capital city is not their most populated city. And look at this query. What we're doing is that we have an outer query that returns countries, capital cities. Okay. And now what we're doing is that here in the where condition, I say, okay, only return this row, this particular country, if the population of the capital city is not equal to something. And that something is the maximum population of the cities for that particular country code. Right? I say, okay, you take Canada, and then here in the correlated subquery, look at all cities that happen to be in Canada, compute the maximum, and if the population of that capital city is not equal to that maximum population, then that is the country that I want. This is a country for which the population of the capital city is not the maximum value. So again, an example of we have written this code using joins in the lab, but you can see that we can do it in a little bit more intuitive way, in my opinion, using a correlated subquery. So the basic idea is again the same. We look at each row, and then we have the option to go and look inside of the table again to do some kind of processing, and then go back and then return the row if a condition is met or not. That's the whole idea. Okay. So we have 1 minute for questions. Yes? Yes. Oh, okay, good question. So can we do this using two correlated subqueries? No, yes, that's possible. That's what, just like I mentioned a little bit earlier, joins and subqueries can sometimes be used interchangeably. That's right. Yeah.
How does it work practically? You wouldn't have two layers.
In that case, something that we can do, we can use a subquery in our from clause. Yeah, and then that gives us access to information in the other table. We can do that instead of a join, basically. Any other questions before ending the lecture?